Math is clean, math's easy when you're doing math with Miss Lee.
Welcome to the lesson on section 2.2, the limit of a function. In this lesson, you'll learn about limit notation, evaluating limits graphically and numerically, one-sided limits, and limits approaching infinity. As a side note, in this course, you'll learn about most topics from 3 different perspectives: graphical, numerical, which usually involves data tables, and analytical, which usually involves algebra. Read this notation as the limit of f of x as x approaches a. Informally, this means that as the value of x gets closer to a, the value of function f gets closer and closer to L. Here's a basic example of limit notation in action. The limit of x over 12 plus 1 as x approaches 3 is 1.25. This statement indicates that if we plug in values for x that draw closer and closer to 3, then the value of x over 12 plus 1 will draw closer and closer to 1.25. The connection between the last lesson and this lesson is that, as you've probably already concluded, the slope of the tangent line to a curve at x is equal to the limit of the slopes of the secant line drawn between x and a number that gets closer and closer to x. However, before we can use limits to help us find slope of tangent lines more effectively, we need to explore limits further. Let's look at how to apply this idea both graphically and numerically using a calculator table. Make sure your calculator is set to radian mode. In AP Calc, we'll always use radian measure for angles unless otherwise noted. At first glance, this function appears to exist everywhere, but you know by looking at the equation that it doesn't exist at x equals 0. However, it appears that both sides of the graph approach the same point from either side of x equals 0. You can probably guess what value the function approaches as x near 0, but let's look at how to use the calculator to find it. On your calculator, press trace. Type a number close to 0, such as 1/10, and then press enter. Note the value of y at this point. Then type in a couple more numbers closer to 0, such as 100th and 1000th. It appears that the value of y approaches 1. If you're following along on your calculator, you should repeat this process for some negative x values that draw closer and closer to 0 to make sure the y value approaches 1 from the other side of the graph. This should be enough information for us to conclude that the limit of sine of x over x as x approaches 0 is 1. Write this limit in the margin of your notes and circle it. You'll need to use this limit for something in the next unit. As an alternative to tracing on the graph, you can also use the table feature on your calculator. Here's how it works. On your calculator, press second window to open the table setup menu. Change the table start value to the number that x approaches, in this case, 0. Change delta table to a small decimal value, and here I'll choose 0.001. View the table by pressing second graph. Our table makes it look like the graph actually reaches y equals 1. However, if you use the arrows so that the cursor is over a 1 in the y column, you can see a more precise value at the bottom of the screen. That becomes a 1 if you have to round to 5 decimal places, which is the width of that column on the screen. Use the arrow keys to move left back into the x column and then up to view negative x values, confirming that y approaches 1 as x approaches 0 from the positive side and the negative side. For our second example, consider the piecewise function in which f of x equals 1 when x is not equal to 2, and f of x equals 0 at x equals 2. First, we need to write the problem using limit notation. The limit of f of x as x approaches 2 is written like this. Next, we need to graph the function. We have the graph of the horizontal line y equals 1 with an open circle where x equals 2. And then we need a point representing y equals 0 when x equals 2. If we apply the same principles as in the last example, Imagine picking x values close to 2, such as 2.1, 2.01, 2.001, and so on. The corresponding y values would be 1 each time. Repeating this for the numbers to the left of 2, such as 1.9, 1.99, 1.999, the same thing happens. So the limit of f of x as x approaches 2 for this function is 1. Now let's take a look at one-sided limits. First, some notation. When the number we approach has a plus sign as its superscript, this is interpreted as the limit as x approaches a from the positive side. Start to the right of x equals a, and then move along the graph towards a. When the number has a negative sign as its superscript, this is the limit as x approaches a from the negative side. Start to the left of x equals a, and then move along the graph towards a. Let's practice finding some one-sided limits. The limit of the absolute value of x over x as x approaches 0 from the left and as x approaches 0 from the right. To draw the graph, we have to consider separate cases. When the absolute value and x are the same and when they're opposites. When x is positive, the absolute value and x are equal, so their quotient will be 1. That makes the graph y equals 1 for positive x values. When x is negative, absolute value of x and x are opposites, so their quotient is negative 1. So we'll graph y equals negative 1 for negative x values. For the first limit, the one with the negative sign, y is always negative 1 as we approach x equals 0 from the left side of the graph. So that limit is negative 1. The right-hand limit, the one with the plus sign, is 1 because y is always 1 as we approach x equals 0 from the positive side of the graph. What if we were asked to find the limit as x approaches 0? We'll need a theorem for that. The IFF here is an abbreviation for if and only if. If and only if means that the statement is true in both directions. Thus, if we know the right and left-hand limits both equal L, then we can conclude that the limit as x approaches a will be L. Conversely, if we know the limit as x approaches a is L, then we can conclude that both the right and left-hand limits are also L. In the function from example 3, we found the right and left-hand limits near x equals 0 to be different values. Thus, the limit as x approaches 0 does not exist. When a limit evaluates to infinity, the graph of the function will have a vertical asymptote. The kind of vertical asymptote you're used to seeing is when both sides of the graph approach some type of infinity, as shown in these 4 graphs. Some graphs can have a vertical asymptote when it approaches infinity from only one side. This concludes our lesson on section 2.2, the limit of a function.